Okay, so what we are, let me recap a few things and then we can go along. So we were just looking this. In this, what our target was to look a few things. Number A, I would say, I mean, algebra was not a, thing that we were interested. Of course, somehow I assume that you know basic aspects of it, and of course, for the sake of completeness, I introduced before you. But the more important point was for us to look at the differential calculus and of course of vectors. That was the point. And number C will be something very important that's called integral calculus of vectors, of course. So that's more or less the thing that we are going to learn in vector calculus aspects of the thing. And these are the things that's very relevant in the physical scenario where you are going to study physics. So differential calculus of vectors, I have mostly introduced the concepts before you. And those concepts, I think we have almost introduced things to you. I mean, I don't think so. Last time, I think, let me also write a few things in the last lecture. So in the previous lecture, we studied, like, the idea was to construct a, you see, let me again say to you, like, two more important things that we are interested in. That's scalar fields, and the second one will be a vector fields, right? So and the example of such field is a temperature field, right? And this one is something like heat field, right? So these two were the examples for those things. And then we also saw that you can form an operator, something like which you call a vector differential operator, which has three components, something like this, right? And you can play with this operator on a scalar, and this is called like a vector function. And this is your gradient is defined gradient of t, that's what you call, right? And then you can again say that since you have a vector field too, you can also combine something like this, and you call this is basically a scalar quantity, and this is basically your called divergence of H, right? And then again, when you have H as a vector field, you can write something like this. This is a vector quantity, and you call this as a curl of H. So you see, by looking, let me just say, I mean, by looking this set, you can see that basically you have some operations with the associated, the differential operator del, right? This is a vector differential operator. And then the idea was to, can you go for further one step ahead, right? And the one step ahead was to construct the second derivatives. Right. So once you construct the second derivative, what sort of second derivatives you can construct? You remember we have a scalar field, and then you construct a vector out of scalar field, right? And with this operator, right? And then you can again do something like this, right? You can take a dot product of this and this, and but what this will be, you have seen, right? This generates a scalar. And the name that I've given to you, this one was something like, it is also a vector with this component. Let me take another slide. No, this part is not. Okay, so this has the component. It's called Laplacian operator, which you will also find very useful when you are going to, when Mukesh is going to teach you electrodynamics. And then again, I said, you see, you can construct something like this, a vector, and then you can again form a something like this, right? This you can also do. And what this will be, let's see, this is a B. First one, let's say this one was A. Okay, so what you can get from this? Right, what was the answer? This was curl gradient T, right? And this was 0, right? You have seen that you have write down this in terms of component. So you have been advised to take like, this is a vector, this is a vector operator. So the homework was for you to break down in the determinant form and try to see the component. What I did, I try to basically look at the let's say Z component of it, and Z component of it, so I have proven that this turns out to be 0. Similarly, you can add for others too, but the homework for you was, as Mukesh was also advising to you, right, that you can form a basically cross product and write down a determinant and see things. So this gives you something like one important, I would now introduce a theorem to you. That's it. Somehow my board have something. Eraser is not working properly. Okay, so what I was saying, that basically there is a one theorem that I would like to introduce to you, and it's very important in physics especially. Of course, you see, I'm not going to prove these theorems to you. Basically, a couple of theorems I will introduce, but the proof I won't do it here because I don't think so that's going to be necessary for you guys right now at the moment, especially. But if it turns out to be like in further, I mean, we will see that if I can derive it in a due time. But I will just introduce a first theorem, that let's say first one, and this says something like, if I can write something like this, del cross A 0, then if this is true, then there exists a scalar, something like psi, or you say T, because you see, I have been maintaining the scalar and vector, something like T stands when you have a temperature field, and H stands when you have a heat field, I mean heat which is propagating through temperature difference. So that's I prefer to maintain throughout all these lectures, because of the fact that you will not feel the output. But you will see that people use these sort of symbol, especially in physics. But let me, I mean, not write it because of the sake of like something when you are going to study quantum mechanics, and then you will see people frequently use this as a basically your wave function, right? So for those sake, I think you should not get confused even if I right now use this also. So this has nothing to do with that wave function that you will study in quantum mechanics or anything. So that's what I would say right now. But you always keep in mind there exists a scale. For then I would even just erase. Let's be complete side. So then you just say something. There exists a scalar T, and such that you can always construct A out of this scalar. You are seeing my point, something like this. So this is your theorem. Like if you will see that I mean grad of something like curl, you say this is a curl operation of something, a vector A is 0, then you will always find there exists a scalar field psi, I mean T, such that you can, this A can be written as a gradient of this function. So that's your one theorem. So you see, we are still looking to formulate a few things, and those few things are what? To construct the second derivatives, right? Because of the fact that you will notice shortly why I'm doing so, because all these things are very helpful when you are going to study your problems and other things. So right now we are just moving into formalism, and very important formalism that's are very important in physics. So, and then we have also seen that you can construct operator, something like this, right? It will be a vector operator, right? Because of the sake. And then you can also see, you can construct a operator, something like this, right? So what this will be, what was the answer for this? 0, right? So that's, we have seen that you can construct this operator and you can find something like this 0. So what that means, you are also aware of that, what we call this, right? When you find something like divergence of curl 0, so that people also write something like this, divergence of curl H0, right? So it is something like stating now again a theorem 2 here, TH2, and TH2 will be something like, if I can write del dot A 0, if I can write del dot A 0, there exists a vector H such that A is what? Grad curl of H, right? So that's another theorem for you. Proof, of course, I said for some reasons that we are not right now looking into it. And then the last one, we have formulated a second derivative, something like, right? So I also said to you that there was ambiguity while writing this derivative, right? It just happened because of the fact that you chosen to write by looking a formula which involves just vectors. These are all vectors, right? These are all vectors and they are not differential operators, right? So that's why it happens, right? Because you have to be very careful when you write operator and when you choose vectors. So we have seen, right? And I think one of you have pointed out that basically it turns out to be something like this, minus, so this grad square was something coming somewhere here, right? Just give me a moment. Yeah, sorry for the disturbance. So yeah, so we have seen that basically you were getting this operator something like this side, and this was not a correct equation, right? So I have suggested you to write down in a proper fashion and figure it out by yourself. The correct answer will of course be something like, right? So that's what your answer. Okay. So this was till last time in, so we are done with our differential calculus objectors. I have introduced all identities I feel like necessary for you guys to look things forward. So the today's topic will be very much something like, I would introduce the vector calculus. Sorry, I would say I would introduce the basically the integral calculus with vector. So yeah, I mean, give you a couple of questions right now, maybe 1-2 questions. If I have, I can put before you. You can take a look. That could be, of course, nice for you. So let me. Yeah, I can say. I mean, you see, basically, I have already defined you a field, something like a vector field, which is something like this, right? When I write this, something like it, always I have meaning something. This, suppose you have a field, but for example, I would again address this problem in the way we are looking a coordinate system, something like this, and I measure some point P, right, in this coordinate system which has a position vector r, and the coordinate of this point was something like xyz, right? So r can be written as, you see, you can make this as a r right now. Somehow my razor is not functioning very properly today. Yeah, so okay, so make this R. So then R will be something like this, right? Now I just want you to calculate for me this quantity. Can you do that for me? So what will be the answer? Can I get the answer right now?
3, sir.
3. Now suppose if I have a point somewhere here, right? Let's say this point is r prime, right? You see my point? So the coordinate of this point is somewhere, let's say x prime, y prime, and z prime. And let's say this is p prime. Now I want to write this again. So what will be the answer? Yeah, so you have to think about it. I mean, it's a one-liner, and but you have to little bit thinking is involved, and you will see why I'm not. I mean, the purpose to introduce, I mean, this sort of problem before you is to just lead you into something, because of the fact that your electrodynamics is currently running before you, and you will very frequently notice these sorts of basically divergence and operations with del operators emerging, where you have position vector, you have to multiply, or basically you have to play with the position vector. So this is your homework, and you see, when I give you a homework, it's very essential for you to perform, right? Because of the fact that unless you don't attempt this, the course itself, I mean, it's not very complete thing, right? Because of the fact that I have given you so many things till now, what I remember. I mean, unless you don't solve those things, you will not understand the reality of it, what we are discussing. It's very essential, I would say. I mean, and mostly I think we are done with vectors. For example, what I feel like is important for you, of course, vectors are very, maybe one more class I would take if today we are not able to done things. So one more class maximum, 1 or 2 maximum, a class I will take where everything, I mean, like conceptual formalism, I will put before you. And then of course there will be assignment sessions that that you will see the whole varieties of problems there. You will so that's there you will handle, I mean, many sorts of problems, and you will also you will also find those things in our website, basically, where we will upload things for you. But before we do that, I mean, you have to, I mean, bit 1-2 problems during our class time. You have to also look into it, and the homework is very essential for you to carry on. So this is a question for you: how you now calculate with respect to this r prime. Now you again take one more problem. So this let's say problem 1, let's say problem 2, and now I just want to define a new vector from here to here. You see my point? So you define a vector from origin from here to this. This is like this is like this, and this is like this, right? So you define this new vector and something like this. You will see these notations when you will study electrodynamics, why this is important. So this is a difference vector, something like this, r minus r prime, or right. So you can just define this vector like r minus r prime. Now I just want to again write something like this. So can you calculate this for me right now? So is there any problem with you? I mean, if you are not able to calculate, it's okay right now. Are you trying to get it, what I'm trying to put before you? So for example, when I say r minus r prime, what will be the r minus r prime? First, tell me what this vector is exactly. How you can write it right now?
So x minus x dash plus y minus y dash plus z minus z dash. It's x cap y is.
Right. Now, since you have defined the vector r, I just want you to calculate this thing, right? So you will also notice in a while that, let me take another slide. You will also notice that, for example, when we write a vector R, and we are somehow breaking this vector into the components, like you see the way I have introduced you the coordinate system. I have introduced a coordinate system, which is your basically Cartesian coordinate system, right? Till now we are very much willing to introduce things before you in a very simpler fashion, and this is the most simplest form of a system that you can have, where you can measure things. You don't have to look for angles and things like that. They are mutually orthogonal axes and things like that. So you will see always there are various symmetrical aspects, right? When I say symmetry, for example, geometry of a problem could be a very important factor for you. What I mean is, if you have a, let's say, surface something like this, which is a spherical in nature, or even say in two-dimensional, which is circular in nature. Maybe let's say this is a circle, right? And maybe when you say in 3-dimension, it becomes like bulky. I mean, it becomes a ball of solid. So it becomes a circle. So you will immediately notice that for such sort of problems, I mean, choosing a different sort of way of defining the coordinate system, basically your spherical, what people generally knows today is spherical coordinate system, or maybe that's what it is in this context. So spherical coordinate system would be more appropriate to introduce before you. We will also look into those things, but till now, the way I'm just putting things before you, you can properly handle things in your Cartesian coordinate system. So, okay, fine. So what I said basically, yeah, so this vector R, you have to calculate these things for this vector R, right? So I would, what I would say basically, I want you to write down this for me. Answer I can give it to you. I think I have this in my, with me right now. So this turns out to be something R cap, and this you have to figure it out by how you can formulate this, right? Okay, and then take one more question. Now, if a vector field is given by some, yeah.
Sir, can you repeat what you said, sir?
Yeah, I said, for example, what I said in case of, I mean, till now, the way we are studying things, I'm defining a coordinate system to you. I'm writing a position vector. And the coordinate system is very much like your Cartesian coordinate system, where things are very much like, you see, you define these perpendicular to each other, all these axes, right? So that's your Cartesian coordinate system denoted by your X, Y, Z. But there could be a very important cases for you. I mean, the geometry, especially, you see in physics, you will always encounter cylindrical or spherical geometries. That's are very much in the heart of physics. So like, you will see that the people have, I mean, somehow notice the importance of those geometries. And when you have certain, I mean, special kind of geometries before you, you need to look, I mean, a better version of your Cartesian system to replace it, right? And you will notice that what are the better versions when we will look into it. For example, you know that how basically a sphere look like, right? The sphere looks like something like this. Now, if just you want to put somewhere on a sphere, like I want to measure some point over here, right? You may notice that how can you do that, right? For example, in your Cartesian system, you only just need a vector R. But here you need some additional things, right? What are those additional things? We will see. Let's not delve into that. We will see. So right now, I'm just introducing, there are geometries, and geometries are very important to look into physics because of the fact that they have certain sort of symmetries. So उनकी वजह से हम देखेंगे कि why those things are very important. So yeah, and then I just said, I mean, you just calculate this thing. Till now, we are still in the very much interested, like I defined a vector R here to you, which has something like X, Y prime, Z prime. So I can also share, I mean, on these identities, a very good literature right now. I have just, somehow I was just looking archive yesterday, and I found, I mean, a paper on basically black hole geometries. So it's not very important for you to right now look into the concept in deeply black hole, but try to see how even these sort of simpler things which you are running right, I mean, which we are teaching you right now, how they are very helpful. I mean, even research publications, right? This is very important. I mean, and you will be very much encouraged to look into those things, right? I would basically upload on our website. You just keep looking on things. You will find there. And the idea for you is to not, I mean, maybe you can look, just read abstract what people are trying to do there. But even before that, I would say you just see the use of these things, I'm just teaching you. I mean, why I just even introduce these problems to you before of the fact, even by looking that paper. Even I feel like it's very important for you guys to know. I mean, at least you will have some idea of how the research is going on right now, right? Even at this level, if you somehow get some sort of idea, it will be very helpful for you in your future times when you further pursue your physics career in long run. So yeah, so you derive this. It's very important for you, I would say. Just derive this, and then I would again write down a vector field for you, something like, okay. And I would say to you, you just calculate the divergence of this. Okay.
Excuse me, sir.
Yeah.
So the first one which you give homework, that one means del dot r equals to r cap. That one, which one is r, sir, here?
Yeah, I said R vector will be this, which will be connecting to these two things.
Okay, yes, sir. Okay.
So you see this in electrodynamics, Mukesh will of course introduce before you in a deep thing. I am not very much willing to delve myself into. You will see why these things are important. It's not my part right now to look into those things. Yeah, so your questions are clear right now. 3 questions you have. The number 1 was I said what will be the something like this, which is something like this. And then the second question was something like this. Now, if I define a vector R connecting these 2 points, how do you calculate this gradient? And now the third question is how you calculate a divergence of this vector field, which is again is a function of vector R in some fashion, something like this, R cap by R square. You will also see how these problems are very important problems in physics. Somewhere or anywhere you are going to always find these problems, whether in your competitive exams or your interviews or even research articles, writing, calculating, very important. Okay, fine. So I have given you a couple of problems for your sake. I think you should look into it. Right now, let's look at the integral calculus of vector. Just give me a moment. Yeah, I will again share because of the fact that I somehow feel that there was some bug. So these things are not going on. Yeah, fine. Yeah, so what I was willing to introduce, that basically integral calculus. Right. So the idea was to, you see, when I defined before you the operation, something like this sort of operation, right? Del dot V or del cross V associated with the vector fields. You see, this called divergence. And this is called curl. And you also know that this is associated with something like flow. And this is associated with something like the rotational aspects of a vector field. It's somewhere embedded in your mind, and somehow you have been always keep on listening these words. So we are also interested to look into right now the aspect that how these things are basically emerging through basically when you try to integrate those things, right? For example, when I say this is divergence and this is something like associated with the flow, then you can always cross questions me. Why, how can you say that, right? How you know that the divergence will be associated with the flow, and how do you know that the curl will always will be associated with the rotational aspects, right? I just want to answer those questions in more detailed fashion, but before we do that, we just want to introduce before to you, like, how do you integrate till now what we have just known, right? For example, you know the integration, right? Like, how do you integrate, right? It's from a point one to let's say I have a point one and I have a point two, and you see I'm just still in a two-dimensional plane, and I define a curve something like which runs from point one to point two, and I have a function something like some complex function of x, and I just want to write down that the total change associated with this function moving from this one to point two. So you will see that the how that could be done. You see the total change can be calculated by breaking this curve into many segments, something like this, and thus calculating this this and summing all over, right? For example, if this is something like a quantity delta Si, or maybe S1 for the first sake, right? So I can define always fx delta S1 and something like fx delta S2, or even I would mostly say write I index with this two, so that it will be more nicer to represent, and on so on. So you will see you add all these sorts of segments, and then this will be effectively equal to something like fs fx ds. I mean, the way you write an integral. So it's a basically limit of a sum, right? Limit of a sum. That's the way your integral is defined. So what we are basically interested in to look into basically the limits of some sort of limit of a sum particularly, but in terms of vectors, right? And in terms of the operation associated with vectors. For example, I said to you that you have a thing called, let's say, scalar field called, let's say, T is my scalar field, right? That's what we are till now we known about scalar field. It's a basically temperature field, and the temperature contour, which I have also introduced, that is maintained in some temperature. And I said you can construct a vector field, something like, you see, I have a tendency of writing psi too much, and you can avoid that. So yeah, something like this, and you construct a vector field. Now the point was, you see, this gives some sort of change, right, in your basically your scalar field, which is given to you in some direction, right? And what was that direction? What is the direction of this? How this point out? So I assume that you guys should think about it, what we are discussing, right, from day-to-day class. It's very important. And sorry. Yeah. So you see, you get some direction. So what my idea was, when you see introduce a calculus, I mean an integral calculus before you, that means you have to be something, you have to integrate something, right? That's what the idea. So for example, if I have a vector quantity which is something like this, and I just defined a curve which is going from point 1 to 2, right? So you also know that for a given field, that how the direction of this quantity is, right? For example, how this point out, right? It's a direction where the maximum rate of change is happening, right? And which is turns out to be the perpendicular direction. So, and suppose this is pointing out along this curve at some point along some direction, something like this, the way of arrow, right? And let's say some small element here is something like associated with, let's say, ds, right? Now I ask you a simple question, right? For example, I just want to go from this point to this point and calculate the, you see, this gives us some change in this field, I mean the scalar field. I just want to calculate the total change which is happening because of the fact that I'm traveling some distance along this curve, right? So this curve is still defined in, let's say, basically a 2 dimensions, or I'm not talking about surfaces or anything like that till now. So I just want to move along this curve, and you will notice that the curve is basically, you can always eliminate one variable. It will be always a one variable integration, that you will also notice. So I just want to move from here to here. Then how can I just sum over all these integrals and calculate down, right? I said, for example, I want to write down an integral of this form, something like this, right? And I want to travel from point 1 to point 2. And you see, this is a vector quantity, right? This ds, this line segment, will always be a vector quantity. This will also have a direction. And I just want to write down this integral. Let's say I call this, let's not call it anything. So how do you calculate these things, right? So can anyone tell me that what will be the answer? It's not something I knew that I'm asking to you. It is something that you have already seen that, and it's very easy to get this, right? And I would again remind you something what we have done, so that you can figure it out by yourself. Reminder. So what was that? Basically, I said basically, right? You remember that my scalar field was defined through my temperature contours, which were maintained something like T1, T2, T3. On these temperatures, they were maintained, right? I said I moved from here to here, and the coordinate of this point was something like this, right? And the coordinate of this point was something like this. You see, I somehow today want very much willing to conclude this, at least. Of course, the definition of this few basically integral calculus, I mean theorems that people know about it. And I don't know that if I can take a long class today because of the fact that I'm not feeling very well. So if somehow I stop in between and don't feel like to teach further, maybe we can, if I could, maybe someday I can take extra class, or I don't know. But if it's not happening today, maybe next class I will try to take a long class and try to conclude things. So I just said to you, you just go from this point to this point, and these 2 points are separated in space, something like this. The coordinate of this point is xyz, and the coordinate of this point is displaced in a very small infinitesimal displacement, where delta x by delta y and delta z. Right now, I just said that you write a quantity which something like this, right? And this change will be how much this change will be. Now let me again say to you that basically what even Mukesh also said that time, that basically it would be better if you write something like this way. For some regions, you will notice very clearly, because of the fact that even I'm just going to introduce, you will always notice that it would have been better if I don't write this symbol. Rather, it would have been better if I use this, because of the fact that you are so much compatible with this. So what will happen if I want to write, for example, let's not again say df, but since we are again taking a scalar field which is t, right? So let's always talk in terms of t. So always have consistency, right? It's very important to be consistent, because otherwise you will lose track what we are just. Yeah. So I said you replace with df, and df was how much? Do you remember how do I write these changes? Now you have to tell me. I have guided you so much. Someone has to speak up. How can you write df?
Del f by del x into dx.
Del f by
Del f by del x into dx.
no, talk in terms of full way, right? Because you see, your point is specified by 3 coordinates, right? X, Y, Z, and x plus delta x, y. So it's like the position is just defined by x, y, z, not only x. So isn't it similar to something like, you see, again, I just want to write it t. So you write it t, right? So it's a big T, but never mind. So isn't the same thing, right? That's the way we have written down, right? If you recall your previous lectures. So you just notice that this thing, I mean, the change in this quantity, that your scalar field T going from this to this, which is separated by infinitesimal changes, delta x, delta y, delta z, can be written as a dot product of a gradient operator and a displacement vector, right? So I just want to integrate along this as a whole path. So what I will do, I will just replace this to this with this, right? So if I take this is my first equation here in context of vector calculus, right? You name your equations very properly when you make your notes, right? That's very important because they are all connected things. And since I am just not keeping track of that thing very efficiently, you should. So in vector calculus, I mean, integral calculus formalism, I'm just reminding this your first equation. And so what I mean is basically by integrating over whole curve, this quantity is just similar to integrating this quantity, right? And what this integration will be? Can someone tell me? Now you have to tell these things. These are very simple things, right? They're nothing special. It just happened. You see, you are very much familiar when like your +2 things, right? When I said to you indefinite, even I don't even give you limits to, I mean, then I just say this is an indefinite integral. You immediately will say, answer me this, what will be this result. But for example, here, going from here to here, I have just changed a few things. What are those few things? That there is this thing, and this is a scalar field. That's of course a bit not as straight as this was. This was a function, but you see this, there is not much difference because of the fact that this could be a scalar function too, right? It's this field could be represented by a scalar function which could comes in terms of x square, right? So it's not very much differentiated by that integral. So what this is, can you tell me? Cannot you write something like this, right?
Yes, sir.
Right? So it will be just the end point. I mean, the limit at this end and this end, right? That's what this whole thing boils down to. So this is your, I would say, this is your first theorem. I mean, this is a theorem in context of, I mean, gradient. And so that's all I would right now say to you, that this theorem basically. And one thing I can also point out to you right now, that basically in going from this point to this point, right, from point 1 to point 2, you have not closed the curve, right? The curve is still an open curve. Now what happens if I just merge these 2 points and make this curve close? What will happen? Can you tell me?
Sir, 0, answer will be 0 when we take integer.
Yeah, so that's exactly is the case. I think others also follow too, right? When do you follow? Others follow why this is so?
Yes, sir.
Yeah, you see, because of the fact that we loses the distinguishability between point 2 and point 1, right? Because then point 2 is nothing but the point 1. Where you started, you ended same point, right? So it has to be 0. So that's basically for closed curve, this integral will always be 0, right? For closed curve. It is very important theorem. It is always asked many times in your examinations or in your competitions for closed curves, especially. For closed curve, this holds, right? This turns out to be 0. But when the closed curve is not closed, the answer is, of course, T2 minus T1. Okay, so I have introduced one thing before you. Now, just let me introduce the concept of concept of flux. And for some reasons, you see, I just said that I just want to, I don't want to move too long today because of the fact that somehow I'm not that well today. So somehow I will just introduce a few things before you and try to, I mean, motivate this concept especially. And then the mathematical, since I have to, I'm very much willing to prove here a few things, I mean, especially the theorems. I mean, then of course, maybe a couple of examples would be nice to do it here. So I think that would again require some time, which I'm not very much willing to go for long today. So I would just introduce basically a concept of flux by introducing a vector field to you. So you remember last time that when I said to you that let me take a slab of some solid material which binds a surface, right? Suppose you have a slab of solid which have a surface C S, and you see I am just taking very conventional definitions where people write the way they write closed surface. So this is your closed surface, which encloses, of course, a volume V, right? Now in this closed surface, I can have my vector fields, right? It has been always, you see, the concept of flux has been developed in the context of fluids, especially liquids, especially. But this is easily generalized to the case of where even nothing is flowing itself. For example, electric field, right? So you will notice that, I mean, that will be coming to your electrodynamics, but I'm not taking in that context. I'm very much interested to take in some other aspects, right? You see, I'm also willing to teach you your basically thermodynamics and StatMech, and so there is some I'm just trying to be coherent when I'm just taking this concept further to your thermal physics or your StatMech. So where you will always encounter your heat fields, your temperature fields. So those are very important two things for you to learn in thermal physics, right? And so by introducing those two fields here right now for you, I have somehow, made myself a bit in a comfortable position where I don't have to invoke so many new notations and so many new things before you and introduce things before you. So I said to you, in this slab, you can take temperature contours which are defined by some particular temperature, let's say 10 degrees Celsius or 20 and so on, like, right? That's one. Let me write, for example, T1, T2, and T3. Now I said basically these contours are basically designed by a number, and they are basically a scalar fields. Now what happens if there is a mismatch of temperature in this slab itself? And you will see that, you know that, right? What happens if a body, let's say A, is in equilibrium within body B, and B is in equilibrium with the body C. So what happens when you say A is in equilibrium with B? What do you mean by that? You see, this is your first principle of thermal physics, right? We will see these in details. And this is also associated with the name in thermal physics. And what is that name? Can someone say to me? Zeroth Law of Thermodynamics, right? This is not as popular as the first law and second law, and even that's why people even don't take, I mean, they don't speak of it much, but this is somehow the formulated firstly, I mean. But yeah, we are not looking thermal physics. You just be cool about it. We are not looking thermal physics. So we are looking itself vector, right? So I'm just motivating that why basically we are studying these things. You are going to encounter these things somewhere, right? So you will see as the temperature temperature difference established in this lab, there will be the flow of heat, right? And heat is a vector quantity, right? And it will flow. For example, I want to ask you a question. I just want to define an area here, something like this. And I just want you to answer me something like how much heat is flowing out of this area, right? So I just want to ask you something like how much heat is flowing through this area. This is also a vector thing, right? Area will also be a vector, right? And of course, this is defined through a surface. So you can always put a surface here, right? So you see, when I am just putting this integral and writing this, you see, you don't get confused. Don't get confused. And what I mean by that, you don't think that this is a very special kind of integral. This is what I mean is that basically this stands for something like this. You see my point? And when I write something like this, you always think that this is something like this. So you have to integrate twice here, you have to integrate thrice here. That's what it means. So here, this is a shorthand. So people don't want to write it too much because this is a cumbersome to write, but this will be something like this. So, I think I would now very much willing to stop it here by just introducing these things to you. We will calculate this in next classes. So I was just now open for a couple of questions. I mean, if you are willing to ask me right now. Otherwise, I will wind up. Yeah. No questions? Fine. So then thank you very much for joining today's lecture, and we will keep on continuing this, and maybe next class I will wind up your vectors, whatever, the concept is required for you. That's what the purpose is. And these are very important concepts for you to know right now. So, and then the next step is to deeply follow the problem set that I will provide to you. And so that's that for today. I think thank you for joining to this class, and thank you very much. Yeah.
Thank you, sir.
Yeah, thanks.
Thank you, sir.